Well, thank you. All right, welcome back. My name is David Malin, for those of you joining us for the first time, and this is CS50, and this is the continuation of week 0. For those of you who may have missed Wednesday, know that we still have some syllabi outside. No more cake, but if you did in fact miss Wednesday, do notice that on the course's website is, as will always be, this is not your typical high school computer science course. So that there is what you missed on Wednesday. So in the future, you will find that the course makes available its videos in Flash formats, QuickTime formats, as well as in MP3 formats on the course's website. So do take a look at that. So we've been hard at work over the past couple of days, particularly one of our CAs, who actually is an alumnus. He lives in New York. His name is Welly. You may meet him in the virtual terminal room over time. And we've implemented what we're now calling Shuttle Boy Voice. So you may recall, and you may in fact, if an upperclassman have used before, this program called Shuttle Boy. It's a good 12 plus years old now. It lives via this link on CS50's own website here. And let me actually grind to a halt here. All right, let's change to this. Oh, so what you will see in a moment. Oh. All right. My name is David Malin, and this is CS50. Welcome back to week 0 continued. We will crop off of the video everything that just happened. If you missed Wednesday's lecture video, know that it is available online. I won't belabor that particular point, but I will draw your attention to a little application that we've been working on. So for some time, there has existed this program called Shuttle Boy. I'm, say, at Memorial Hall. I need to get back after class to the quad, so I click 2 links, and voila, there are the next several shuttles I can get to. Well, we thought it would be fun to take things to the next level this year and to implement Shuttle Boy Voice, the new and improved version of this same idea. As you may recall from Wednesday, we were lucky enough this year to secure 617 Bug CS50. It's not quite yet in production. This is really just a sneak preview. But in a moment, I'm going to turn this microphone on, and we're going to make a phone call together and see who here picks up. So I'm going to go ahead and turn on my speakerphone. We're going to dial and see what happens here.
This is CS50 for Shuttle Boy. Press 1 for Crimson Dining. Press 2 to start over. Press 0.
I'm going to press 1 for Shuttle Boy.
What is your origin for Quad? Press 1 Nether. Press 2 Boylston. Press 3 Lamont. Press 4 Memhall. Press 5 to start over. What is your destination for Quad? Press 1. The next shuttle leaves in 5 minutes at 11 p.m. and then at 11:10 p.m., 11:20 p.m., and 11:30 p.m.
So you're going to be here a while today, is perhaps the immediate takeaway. But so that's not a bug, that's a feature. So we just dummied it up with some data for demonstration's sake, but it should debut for all of you this coming week. And notice we've optimized for the most popular stops. So if you want to get on, for instance, at Pound Hall, it's not going to happen with Shuttle Boy Voice. Quad, Mather, Mem Hall, Lamont, Boylston, all the most popular stops will be optimized in that interface. So more to come. Why do something like that? Well, frankly, sometimes, as you'll see perhaps in this course or beyond, you do things just because you can. And by course's end, will you be able to do that and much more? So today is ultimately about laying the foundation for the semester. And this semester is about computer science, it's about programming, but that sort of begs the question perhaps on day 1, what is the latter? What is programming? Can someone in layman's terms give us an answer to this question? What is programming? You don't want to be down here because I can see you much more easily. Yes?
Writing a set of instructions to the computer.
Okay, so writing a set of instructions to a computer. So a computer is just this fairly dumb device. It's a mechanical device that literally can only do what it is told. So programming is ultimately about telling a computer what to do. Now, how do you tell a computer what to do? Well, in this course and in programming and computer science, we don't mean you just point and click and choose this from the menu and at that high user level, but rather how do you actually go in underneath the hood and make all of that possible? Well, you do this with programming languages. C is the one we'll focus on in this course, and PHP and JavaScript and C# and a whole bunch of others. The history is littered with dozens, hundreds of programming languages, some of which are very much still in vogue, some of which have partly died off, some of which really never saw the light of day. So today we're going to focus on programming ultimately, but not by way of C, not by way of Java, not by way of these textual languages that, while powerful ultimately, and the languages that we'll use throughout the semester, they're not quite the easiest thing to get excited about at term start. In fact, what I'm going to do here in just a moment on my machine is pull up a little program that comes with Mac OS. You can do something similar in Windows, and you'll see how to do this on your own computer before long. But this is a terminal, and what it ultimately gives me access to is the files, the programs underneath the hood on a Mac, which is essentially a Unix-based computer. So what I'm going to do, just to underwhelm you here on day 1 of 2 so far, I'm going to go ahead and write hello.c. So this is a text editor. This is like a geek's version of Notepad or Microsoft Word, but much simpler than the latter, certainly. And what I'm going to do is something like this. So include standard io.h, whatever that means. I'm going to say int. I'm going to say main. I'm going to say int argc, char, star, argv, a couple of brackets and a parenthesis. And then in here, I'm going to say printf. Let's say hello, comma, world, and then whatever this \n thing denotes, and then a semicolon. So it's really hard to get excited if this is what you've got in store for you throughout the semester. Plus, what is int? What is argc? What is char? Why all this syntax? Well, it's a very fair question. It's really not intellectually all that interesting. We do ultimately need conventions. We need a language. We need some basic definitions of how you express yourself to a computer. That's really not interesting here in week 0 thus far. And so we'll quickly move away from this, but just to, again, as promised, underwhelm you, now I have a file called hello.c, just like .text or .doc. The .c is just a convention. I'm going to run a program called GCC, which is a compiler. If you're familiar with Visual Studio, something like that, it's the same type of program, but in a Unix or Linux environment. And I'm going to say to the computer, compile the stuff I just wrote. In other words, turn it into 0s and 1s. Now, the fact that no messages got printed is actually a good thing. So a week hence, when you're actually playing with C for yourself for the first time, if you get a message at that very first point, damn, means you messed something up already. But that's OK, because much of the process of learning and in doing interesting things, frankly, will be tripping over some basics over time. Fortunately, I've not put my own foot in my mouth here yet. But there's now this file. It's cryptically named a.out, just a stupid convention someone came up with years ago. We can change this ultimately, and we will. But inside of this file are a bunch of 0s and 1s that ultimately this computer, this Mac, this Intel Mac, can understand. So I'm going to go ahead and hit Enter, and voila, your very first computer science program. Thank you. All right, so not terribly exciting. And the thing is, we don't need to focus so much on just these basic things like parentheses and semicolons. All of this is completely uninteresting. And we'll get there, but you'll find that it's really not such a big deal, and it begins to come more naturally. But today, we focus, for just this week 0, on programming itself and what it means to make computers do what you want, but doing it in a much more intuitive way. And we do this, as promised on Wednesday, by way of this graphical language developed by MIT's Media Lab a couple of years ago. It happens to be called Scratch. And what we'll see here is another demo of what you saw briefly on Wednesday. And this one I will give you, not one that I myself have made, but a former teaching fellow of the course. I give you, by way of this demo, Raining Men.
Just about half
So hopefully much more interesting than hello world at the command prompt. Now granted, that was made by a former teaching fellow. In fact, one of the stars of the football team. So realize we do get all types here in CS50, not those that I might have recalled from my own high school. But this one is clearly more presentation oriented than it is interactive. And a lot of what using computers is about is taking input and then producing output, actually interacting with a human. So why don't we do just that? And in fact, lest we send the message that only teaching fellows can make things that are this much more interesting than hello world, let me show you something that was made by a former CS50 student. But for this, we need one volunteer to come on up here and stand before my keyboard. Yeah, yep, in the back on the edge there. Come on down. And you do have to be comfortable again being on camera, since what you don't see happen is the signing of legal forms off to the stage once we're done with demonstrations like this. So what I'm going to do is bring up a demonstration. This one was by Andrew Barry. This next one is by Ann Chi. And this one, no, come on, no turning back now, may look familiar if you've played a little something like this before. So some of you might have played DDR or these kinds of coordination games. Maybe not. If not, it's better for the demo. So in a moment, and what is your name?
Jonathan.
Jonathan? David. Nice to meet you. And they. So we're going to hit space to begin. And what's going to happen is music's going to start playing. And as the instructions here say, you're going to have to hit the arrows in lockstep with stuff that's flowing up the screen so that it overlaps the shapes. And then we'll keep track of your score and just how awesome, cool, good, or boo you are. Ready to go? Arrow keys down here. Here we are.
That's how long I've been on ya. You know how long I've been on ya. Since Christmas, don't act for long ya. Since over the icy toners, don't act like I never told ya. You know how long I've been on ya. Since Christmas, don't act for long ya. Since over the icy toners, don't act like I never told ya. Never told ya. Never told ya. Never told ya.
How about a big round of applause? That was pretty damn good. Nicely done. Here we go. So how does one go about writing this stuff? Well, the interesting question today, see, legal form, there we go. So the interesting thing today is going to be to try to dissect intellectually what's going on, right? These things might be fun and they might look silly, but there's really some interesting stuff going on underneath the hood, right? There's some randomness going on there. The game is not always the same in this particular case. In the previous case with Raining Men, there was clearly synchronization. There was lots of stuff going on at the same time. And if you think back just a moment ago to what I did at the command prompt, the textual interface, it's hard to imagine how you could possibly coordinate all of those several things going on when I've completely underwhelmed you thus far by just printing a simple instruction to the screen. And I'll give you a quick teaser too of, in a little bit, of one that I wrote that we'll use for the sake of discussion, if only because I understand what went underneath, what's underneath the hood of that one best, and that one we'll see is called Oscar Time. But first, let's consider, outside the context of this thing called Scratch, what really programming is all about. Well, let's pick something completely silly. So waking up in the morning and putting on one's socks, right? You've probably, hopefully, never really thought hard about this particular problem. You just do it. But suppose you were trying to instruct a computer to do it, or maybe more concretely, a robot to do it. You kind of have to think a little harder. Now perhaps I've raised the bar to volunteers a bit higher, but I need a volunteer for this thing as well. Yes, come on down. And you two will be on camera and shoeless. So I went shopping beforehand. Turns out you can buy some amazing propaganda at the Coop. This is ultimately going to be about this algorithm here. Oh, come prepared. Thank you. What is your name? Josh. Josh. All right, Josh, come on over. Come on over to your chair here. We'll need you to take off your socks. I kind of splurged here. We went with a few different styles here today. So these here, they're all clean though. I thought for a moment maybe I'd just go home for this, but then I thought that might not go over so well. So we have some H branded socks here, which we'll put, say, in the sock pile. I also got some more sporty socks if this is what your preference. So we have these sort of low-rise type socks saying crimson. And then these were actually my favorite. So because you know there's some tourist out there walking around in these somewhere. So we also have a pair of these. So an algorithm, ultimately, as we'll see in just a moment, is a procedure. It's a program, but it's not necessarily written in a specific language. And in fact, what we see here on the board is what we'll call pseudocode. It's not quite code. It's not programming code. It's certainly not zeros and ones, but it's kind of a cross between something that's very succinct and logical, and it's also nonetheless very human readable. And so throughout the semester, before we sit down and start typing things away at a command prompt like I did, or even dragging and dropping, it's often worthwhile thinking about how could you express this program in just English or English-like syntax, because then you can work through the logic. Then you can think through, hopefully, some of the bugs, some of the corner cases, and then proceed to implement that algorithm. So we're going to go ahead and use Josh here for the sake of execution, and we'll see if we can't tease apart a few programmatic fundamentals that will then recur in much more traditional contexts than this one. So Josh, if you would, perhaps think to yourself the following. Let socks on feet, all one word. I seem to have used this underscore notation just to tie it all together as one string. Let socks on feet equals 0. So this is easy. This is a variable, right? Just like x and y and z in high school were variables that stored values, so is socks on feet a little more interestingly named variable that is in fact consistent with reality. So we're initializing our program here. So line 2 induces what we'll call, and this 2 might be self-explanatory, a loop. So something that repeats 0 or more times. Now in this case I've used the keyword while, which does imply doing something while something is the case. We'll see terms like for and do while and similar synonyms essentially, but for this we chose this. So while socks on feet, exclamation point equals 2. Now if you don't know what that means, take a stab at what it might mean. So not equal to. So bang equal sign. So computer scientists, geeks say bang, not exclamation point. So bang equals means not equal to 2. So we're going to do the following while Josh presumably has 0 or 1 or maybe even 3 socks on his feet, because we're going to do this while it's not equal to 2. So here's where your awkward role play comes in. Open the sock drawer. Excellent. Look for sock. OK? If you find sock, so this, too, it's bold-faced for a reason. This is a condition, a branch, something that happens optionally if something is true or false. So if you find a sock, have you? OK, then, and notice the indentation here too. So this is something we'll use consistently. This is a matter of style. The computer often does not care if you have spaces, tab characters, indentation, no indentation. And those of you who have written HTML or web pages before probably know that it might look pretty to make everything nice and hierarchical and pretty printed, as they say. But the computer certainly doesn't care. But here, we're humans. We do care. So it's indented to imply that lines 6 on down are now encapsulated inside of what line 5 is telling us to do. So if line 5 is true, if find sock, which he did, then we proceed to the indentation. Put on sock. Excellent. Socks on feet plus plus. This is shorthand notation, and we'll see this in C, JavaScript, PHP. Plus plus, as you might infer, just means increment it by 1. So socks on feet now equals 1. Look for matching sock. And this we might call a statement. Anytime it's just sort of matter of fact here, we'll call that a statement. OK, you've looked. If you find a matching sock, then indentation, put on matching sock. So far, so good. Socks on feet plus plus, close sock drawer. And now notice I'm not going to proceed to do anything with line 13, because line 13 is exclusive with respect to 9. So if I did 9, I don't do 13. Similarly, if I did 5, I don't do 16. And now what do I go back up to? Well, following the logic of the indentation, I now go back to line 2, and I check this condition. While socks on feet not equal to 2, what do I do now? Yeah, I seem to move on. So what's next? Well, line 18, which isn't even present, so we implicitly drop out of the program, and we're done. So that was actually very good. And now, if you wouldn't mind, let's restart this. Take off these socks if you would. And now it'll get awkward for me. So I'm going to take, say, this, and this. Did we screw up? Is this program actually correct? Well, let's see. Let socks on feet equal 0. Good. While socks on feet not equal to 2. Good. That is true. Indentation. Open sock drawer. Look for sock. If you find sock, then nice. Put on sock. You will always remember this moment in college. Excellent. Socks on feet plus plus. Look for matching sock. Problem. If you find matching sock, then line 9 doesn't seem to apply. So we go to line 13 followed by 14, else remove first sock from foot. Socks on feet minus minus. So now we're back to 0 presumably. What line do I go back to next? Yeah, so not 5 I heard, but rather, so I'm back up at 2. While socks on feet not equal to 2, OK? True. So we proceed to open sock drawer. Look for sock. If you find sock, then put on sock. So at this point, you're probably getting a little bored, right? Because what's going to happen here? All right, so this is one of these things called an infinite loop. Or if you've never heard of that expression, that's what it is. And frankly, you've probably experienced this before. Whether you have a Mac, a PC, or whatever, you've probably at least once in life gotten really ticked off at your machine because it's kind of just hanging and hanging and hanging. Or the stupid hourglass is just spinning and spinning and spinning, and it never stops for some reason. Well, what is that? Well, technically, it could be any number of things, but it's probably a mistake that some programmer made, didn't anticipate the fact that maybe I haven't done the laundry all that often, and therefore I might not have sufficiently many socks. Maybe I just don't have certain socks anymore because they got torn and I threw them out. These are what we'll call corner cases. And clearly bad, awkward things arise if you don't handle these cases. So in those cases with your own machines, you probably rebooted or you force quit. You pulled up the task manager. All these stupid real world issues that boil down to stopping a program that's caught in an infinite loop. Are there other bugs here that we might trip over? Sorry? Yeah, so there's also some real world problems here perhaps, especially if this is, again, not Josh a human, but Josh the robot, where it keeps saying open, it's an open sock drawer, open sock drawer. Like, what does that even mean? I mean, either the robot's going to start ripping the thing out of the wall, or it's just going to get confused because it's ambiguous. And ambiguity is ultimately a problem too, because what is going to happen in cases that are not so explicitly specified by you? So why don't we put Josh out of his awkwardness here. You get about 6 souvenirs today. They are clean. I can give you a little shopping bag, if not the receipt, if you want. But here we have some nice little Harvard souvenirs. So perhaps a quick round of applause for Josh. Thank you very much. All right. So this is what we did at the command line quickly. And this is what we'll do a week plus from now. This week we focus on things more intuitive. But this is a basic C program, a canonical program. And in fact, it will get much more interesting, much more powerful than this. But what really happened underneath the hood when I wrote this little program? Well, if that's my program at top left, and I ran that program called GCC, the compiler, well, what that compiler did, and it was written by some smart people a while ago, it converts what's kind of looks like English, but is definitely not English I'm used to writing in. It converts it to zeros and ones that my particular computer understands. And this process is called compiling. And this is partly the reason why, if you've ever bought a program, maybe Microsoft Office, you either buy the shrink wrap box that says for Windows, or you buy the shrink wrap box that says for Mac OS, because even companies like Microsoft very often have to essentially write 2 versions of programs, because a compiler, as I hinted at with my own Mac, is kind of machine specific, or at least it's operating system specific. So unfortunately, we don't really live in a world that's as perfect enough whereby Microsoft writes their program once and they run GCC on a Mac, they run GCC on a PC, they copy the resulting a.out file or msword.exe file to a CD and ship it. There's a lot more to it than that. So one of the things we'll talk about closer to term's end is the notion of cross-platform software. Java, one of the appeals of Java, if unfamiliar, is that in theory you're supposed to be able to write a Java program once and then run it on any computer you want. A Mac, a PC, a Linux box, even a cell phone these days. And you'll use a program like this, the virtual terminal room, to which I referred on Wednesday for virtual office hours if you decide to log on. That's actually, you'll see, a program written written in Java because that particular company, called Illuminate, decided it's really expensive and it's really uninteresting for us to have to write our software multiple times just so that we can have Mac customers, PC customers, and so forth. So they went with Java. But there's downsides even to that. So what then are we going to do this week? It is Scratch. And today what we'll do is lay the foundation for just these basic programmatic constructs. But by lecture's end today, will we already begin our transition to C. Your first problem set, which will be posted, as will be typically the case, by 7 p.m. tonight on the course's website. If you're like me, you're welcome to dive in at 7:01. If you have more going on, you can wait a few days because you have ample time for this one. But they'll be posted on the course's website at cs50.net. But let me encourage you to take note of this too. So especially for this first problem set, you'll find that it's rather fun. And in fact, you'll probably get a kick out of sharing or making your roommate take a look at what you've actually been working on. But so that you don't feel completely thrown into the lion's den, so to speak, especially if you're feeling a bit among those less comfortable, we will start office hours this coming week. So no sections just yet. We will start the process of sectioning next Wednesday onward. So more on that next week. But office hours, this list will grow as our 50+ person team begins to figure out their own schedules. We're going to hang out next week on Monday, Tuesday, Wednesday, Thursday evening, 7 p.m. onward in Cabot House's dining hall and in Quincy House's dining hall, where you can bring your laptop, you can hang out for brain break, and a number of the teaching fellows and CAs will be there to help you, to chat with you, and just generally tackle this as a team. So what are you going to be tackling? Well, this here is Scratch. I went to a website called scratch.mit.edu. It works for Macs, it works for PCs. I downloaded this program, and voila, this is what I get. Well, what is this interface? Well, on the left-hand side here, we have these puzzle pieces. And they literally look like puzzle pieces that in a moment I'll be able to drag into this scripts area here. And it's by dragging and dropping these pieces that I will be programming, so to speak. Well, on the top right, we have what we're going to call the stage. This is where stuff happens, as we've already seen. This little cat, by default, this is Scratch, sort of the mascot they went with, but we can change his appearance at will. This is what we'll call a sprite. A sprite, or really, it's what we'll call more technically a thread. A miniature program that you can instruct to do things independently of anything else. And at bottom right here, we'll see all the many different sprites that I might possibly create. So let me go and do this. So control when green flag clicked. So when I, a moment ago, typed that cryptic sequence of instructions int main, main kind of has some implied meaning. This is the main guts of my program. Well, this is sort of the equivalent. So those of you coming from to the course from like a Java background, it's like writing your main method. So this block, just to be clear, has this icon on it that says when green flag clicked. And that's why, if you've been paying close attention, every time I start these demos, I click that green flag. So what does that mean? That means when we click that green flag, this cat, this sprite, because he's currently selected, is going to do whatever the blocks tell him to do that are attached to this particular starting point. So what do we want him to do? Well, let's do something simple. I'm going to click the little palette here for looks. So the MIT is nicely color-coded things just so that all related blocks are similarly colored. I'm going to flip through this and, OK, here, this is interesting. Say hello. So hey, say hello for 2 seconds. And just because it's a little small, that's what that puzzle piece looks like. And notice too, and this is the magic of it, you bring it close enough, it snaps together. Right? It's a lot more easy than remembering, all right, I put the parenthesis and then the semicolon and then hit enter. Right, you just drag and drop, and these things will fit together logically if that makes sense programmatically. I'm going to click the green flag. Wow. All right, so I just wrote what was this a moment ago. Not so bad, but not that interesting in fairness. So let's do something a little more interesting. So let me say something like this. What is your name? Question mark. So now I need a way of actually getting input. So how can I do this? Well, under sensing here, there's this block. Now ask what's your name and wait. Well, let me try and do this. So what's your name? Oh, wait, this is already a bug, right? I've kind of gotten ahead of myself. So let's do this. Hello. We'll say that for 2 seconds. Then ask this, and then wait. Well, let's see. Hello? What's your name? All right, David. Kind of a stupid program, right? I've asked for my name, but I'm not doing anything yet. So let's do something a little cute, perhaps. So looks, how about, let's see. So there's the say block. There's this think block. Let me plug this in. Now, I don't want it to say Okay, well, we'll let it say but then I'm going to be a little cute and say something like, let's say, doesn't ring a bell. And actually, is a little generic. So let's do something even more interesting still. Under sensing, notice that there was this answer here. And if I had actually gotten some help about this block, I would have gotten a little cheat sheet. What does this do? So this programming environment, it's actually very easy to bootstrap yourself because all of the help is right there for you. I'm actually going to drag this. And then notice that the doesn't have to be me manually typed. I can actually plug in this variable. So now I go ahead and say this, hello. What's your name? All right, David. And that's a little cartoon bubble there. Doesn't ring a bell. All right, so baby steps to be sure, and still not all that glamorous. Probably you're not tapping your roommate on the shoulder just yet. So what more can we do with this? Well, let's see if we can't take things progressively higher and higher. And what you'll see is even though a lot of these initial demonstrations are terribly simple, that's what programming ultimately is about, is taking some very basic building blocks and building them, building on top of them, kind of combining them into things we'll start calling functions and libraries so that you don't have to reinvent these uninteresting wheels all the time until finally do you get much more interesting software. Case in point, things like Shuttle Boy, that we don't have to worry so much about these minutiae before long. So there are these things called statements in programming and in Scratch. Anything that is a block that's sort of imperative, say this, wait for this amount of time, play sound, we'll call these statements. And these are just a few examples. So here are two programs. The left one we can figure out intuitively. So when green flag clicked, that example is going to say, oh, hi, world, for 1 second. Then it's going to pause. It's going to say it again. Then it's going to pause. And then it's going to say it again. All right. Rather underwhelming. Let's go ahead and pull up the third version of this, though. And all of these examples you can download from the course's website. Let me go ahead and pull up hi3.sb. Double-clicking suffices. That's the program. Notice there's really not much complexity here. I still have just one cat. But let me go ahead and click play now. Okay, still maybe not roommate worthy, but let's see where else we can go with this. All right, so there's Boolean expressions in programming languages. A Boolean expression named after a Mr. Boole is an expression that in the end is either true or it's false. It's either 1 or it's 0. It's yes, it's no. These two dichotomies. Doesn't matter what labels you slap on them, but it's this notion of true and false. So what kinds of questions might return yes, no answers, true, false answers? Well, is the cat touching the mouse pointer? In other words, is my mouse hovering over him? Because if he is, that could be an interesting mode of interaction. Is the mouse button down? That, too, is kind of an interesting question to ask, because if so, maybe I'll do something interesting. Is something less than something? Well, sometimes it's useful to do numeric manipulations, even in a context like this. And then there's this Boolean AND operator. If any of you are particularly savvy with Google or search engines, sometimes you might realize that you can type, say, David and Harvard into Google search box or something like that to get results that actually relate not to David or Harvard, but both of them, in fact. And so we can merge Boolean expressions into singular units. Why is that interesting? Well, if we can ask these yes-no questions, we can do things or not, conditionally. Just like Josh put on the sock only if he found a match, can we similarly distinguish between different states of our world here? So there's this if block in Scratch at the far left here. So if something, and notice there's this funky triangular shape here too. So you'll find that there are similarities not just with color in this program, but also in the shape of the blocks. So just as a visual cue, what can you put into that placeholder? But it's not just interesting to say if something's true, do this. Sometimes you want it to be exclusive. Do this, else do that. And so there's this if-else construct. Now, sometimes you might want to do this, that, or the other thing. Well, these things can nest. So even though it doesn't look like you can cram another block inside that middle one, else, I mean, it's only this big. How in the world do we fit anything in there? Well, what you'll find is that Scratch automatically adapts itself. It just grows the size of the block if you want to squeeze more blocks into it. So now we have the ability to do things conditionally. Well, why is that helpful? Well, let's take a look at iteration 4 of this. So I'm going to go open hi4.sb. It's not a very interesting program yet, so let me hit play. I'm going to hit it again. This is sort of vacuous truth, right? This is not a very interesting use of a condition because 1's value is presumably never changing. So let's hope I did something a little smarter with version 5 here. This is version 5 of this same idea. So now the fact that we can plug in values from elsewhere, this gets a little more interesting. So this block here, let me zoom in, is what we'll call a pseudo-random number generator. Now to the target audience of Scratch, which is usually people about yay high, so 10-year-olds, 12-year-olds, MIT's teachers don't whip out terms like, now use a pseudo-random number generator to make your cat move. But that's what we're going to call it, right? And we're in this case, going to pick a random number. How that gets picked is actually an interesting question unto itself. And those of you who like mathematics, like theory, I mean, there's a whole world of discovery and a whole world of research that asks the question, how do you make machines, which are by nature deterministic? They only do what you tell them. How do you make a machine like that pick a random number? It would seem to be the case that you have to tell the machine what number to pick, but that would sort of defeat the point of having randomness at all. But in fact, there are ways of doing this, or there are ways of simulating this. And as an aside, you can kind of cheat. For instance, if your computer has a microphone, well, odds are you're not going to be in a perfectly quiet room all the time. So maybe you get some randomness, some random noise by way of turning on your microphone. So there's some juicy areas of discovery there. But for us, we're just going to use it mechanically. Pick a random number from 1 to 10. This has the effect, if all goes according to plan, of the following. Is that a bug? I clicked, nothing happened. It's kind of to be expected, I think, right? OK, that time it worked. Didn't. Did. Didn't. Did. Now, as you may recall, if we do this an infinite number of times, 50% of them will, in fact, meow. 50% of them won't. And we actually had good statistics. So last year was actually a little awkward because I kept hitting the button and the damn thing kept meowing, meowing, meowing. But that actually speaks to the fact that it is, in fact, random, at least in some part. So who cares? What can we do with this? Well, let's see what else we can build on. So there's a way of doing things multiple times. Now, in one of my first programs, I had the cat meow 3 times. It said, play sound meow, wait a second. Play it, wait a second. Play it, wait a second. Well, that's kind of a nice capability if you can tell it to do something multiple times. Let me go ahead and open up this thing here. And again, this is what we just glanced at the slide. It's rather underwhelming. And in fact, it's perhaps more interesting if we at least make it slightly annoying by doing it this way with the sound. And in fact, I'll indulge in what you inevitably will find a fun way of procrastinating. It turns out we don't have to use just the meow. We can click things like import. You'll find that this environment comes with all these various effects. So maybe it'd be more fun to do something like OK, and there's the cat. There's other things too. I think if we go into vocals, we can got this one. So that's not that bad in terms of annoying. So let me do this. So again, note it, and please stop me because we can't go on this tangent too long. So there's 3 tabs up there. And again, this is not interesting stuff intellectually, so we'll wave our hands at it largely today. But I'm going to go back to my scripts now. And now notice, to change the sound, all right, so I'll do this, this, this. But the point I wanted to make was, what do I do if I want to make it do not 3 times, but 6 times? Well, you can duplicate things. So actually, let me go ahead and duplicate it from here. And I'm just right-clicking or control-clicking. Let me get this stuff out of the way there. And yep. So now I have it going 1, 2, 3, 4, 5 times. And actually, let me detach this 6, 7 times. I'm going to drop this over there. And let's just see how annoying this gets. OK. So the point is now not to annoy, but to demonstrate that this is not the smartest approach to telling the computer to do something again and again. If you find yourself, whether in C, Scratch, JavaScript, PHP, just kind of copying and pasting to get your program to do something multiple times, which may be compelling, there's got to be another way. And in fact, there are. There are these constructs, as we saw with Josh's example of looping, in Scratch and in C and in JavaScript and in a lot of modern languages. These things are called while loops or for loops. In Scratch, Scratch, they're called forever loops, or repeat some number of times. So already can you probably imagine how you might integrate these? Well, what about something like this? If we wanted to create that very simple effect of doing something ad nauseum, if we pull up version 6 of this, notice that the blocks I've chosen are when green flag clicked. I then grab that forever block. And to be clear, the forever block is not normally that tall. So notice the mere act of dragging something like this inside the forever loop makes it bigger. And then if I want to squeeze this in, it makes room. But again, everything is similarly shaped. Now I'm going to have the same effect, slightly less annoying. And now I've arguably implemented this with a much better design. There was no reason for the copy-paste. And in fact, if you sort of think about where that bad habit leads you, if you're copying and pasting constantly, imagine how much work it would be for me to go back into the previous version of that program and actually change something like the sound that's being played. I mean, my God, I have to like change it in 6 or 7 different drop downs. Here, I just change it in one place. And so we already have this ability to do things that are a little better designed. Well, what about this thing at top right? So top right is saying when green flag is clicked, do the following forever. Well, what? If touching mouse pointer, play sound meow, and wait 2 seconds, and then repeat. All right, so let's open this. This is version 7. I'm going to go ahead and open this. And just if you wondered how I was doing it before, at the top right, there's presentation mode, where you can zoom in and make it even bigger. So now I hit play. Nothing seems to be happening, but that's consistent with the previous slide because I didn't use the say block. I didn't use the think block. But notice my mouse, if I move it closer and closer to the cat, it's kind of like petting the cat, if you will. Clever? I thought so. All right. So kind of interesting. Let's take things slightly higher. So that's version 7. Let me go to version 8 here. Version 8 is not that much bigger, but now notice what's going to happen. You can kind of see this one coming. All right, so this was me thinking this was really clever. All right, so let me go ahead and full screen it, click the green flag, and now notice he's just going about his business meowing. Okay, that's all good. If I now try to touch him, bad things happen. And then he'll go back ultimately to meowing. OK, so now we have this ability to do things conditionally inside of loops. So already we seem to have a fairly rich amount of expressiveness. We can kind of think about doing something like I did last night when putting that together. I wanted the cat to just meow, meow, meow. And then I wanted to do something optionally. So there, you have loop, you have condition, sandwich it in between, think about what statements you want, and voila, we have that effect. Well, what more can we do? Well, we have variables. Now, variables are useful, certainly in the context of Josh, where he had to maintain state. He had to remember how many socks he had on. Otherwise, he would just keep putting on socks, putting on socks, putting on socks. The use of that variable allowed him to short circuit that loop and terminate as soon as he reached some happy place. Well, what about these two programs here? Count1.sb is at left. So when green flag is clicked, set a counter. That's apparently a variable that I chose. It's better named than x, better named than y, which though you might have used in algebra, really isn't that useful when you're trying to remember what your own program does. So again, a good matter of style is pick variable names that say something interesting. So set counter to 0, forever, say counter for 2 seconds, then wait a second, change counter by 1. So this is Scratch's approach to plus plus. All right, so in count1.sb, we have the following. Count 1. No sound, but I thought it was very clever, too, that the sheep was doing the counting. See, geek humor. All right, so things are more fun with sound, so we'll kill that thing. But it's going to go on up at least until we hit some upper bound. Can you anticipate, maybe if you're coming at this with a background in some programming, what could still happen that's bad here? Sorry? Might only be using 8 bits. Yeah, so actually roll back mentally to Wednesday when we talked about representing numbers. And by default, I kept using 8 bits to represent numbers. Well, if you have 8 bits, each one of which can be a 0 or a 1, that means you have 2 possible values times 2 here, 2, 2, 2, 2, 2. So that's 2 to the 8th, right? So that meant we had 256 possible values you can represent with 8 bits. The number 0, then 1, then 2, then 3, then 4, then 5, all the way up to 255. And again, why 255, not 256? Computer scientists tend to start counting at 0. So we spend one of our encodings that way. So a problem that might arise here is MIT probably made a judgment call somewhere underneath the hood when they implemented Scratch itself, where they decided, you know what, no 12-year-old is going to count up to 4 billion. We don't need 32-bit integers. We don't need integers that are represented by 32 individual bits, maybe just 8 or maybe 16. But they had to make a judgment call. And just as, think back to the Y2K problem, what was that problem? Well, the world had decided in the 1970s, give or take, that you know, this code's never going to be used 30 years from now. Let's just use 2 digits to represent the year. And then you may recall, bad things happened, or bad things were predicted to happen. Certainly expensive things happened when we rolled back from that mistake. So same thing here. Let's not spend the time figuring out just how high this sheep can count. But that, too, is going to be an issue we trip over when you start coding in C and in PHP and in JavaScript, where you have much more control over the representation of numbers and of data. Well, what about count2.sb here? So when green flag clicked, set number to a random number, say the number, and then if that number is less than 6, play sheep. So in English, in layman's terms, this thing's going to do something 50% of the time, but at least now we're going to have some introspection. We're going to see why it's actually playing a sound or not, because it's going to tell me what the number is, whereas before I simply had to guess. So this is count 2, still involving our little sheep here. If I hit play, 6, nothing happens, because 6 is not less than 6. Play, 10, still nothing. 7, still nothing. See, this is where, right, so we could be tossing a coin, and it might keep coming up heads that many times. Hopefully, it will go the other direction 50% of the time. So if we do that an infinite number of times, hopefully the math would, in fact, work out. All right, so those are variables. Well, variables are useful, but only when you want to store one piece of information. But you could just use then multiple variables to store multiple pieces of information. But if you think now, even in terms of Scratch, that each variable right now is its own block, imagine how you might implement, maybe not in a game like some kind of RPG game where you're a character a la Super Mario Brothers and you have to go around collecting things. Any game like Zelda, any game where you go, or even Quake, Halo, anytime you pick up something and have to add it to your inventory, it would probably be a fairly unmanageable program if you had to have a separate variable, a separately named variable for every possible possession that someone in a game might need to carry around. It'd be a lot easier if you could sort of have just a bucket or a satchel, whatever the analog is in the actual game, that can contain 0 or more items. And that data structure, as we'll start calling it in programming, is what's called an array, sometimes called a vector. Also, we'll see fancier versions of this ultimately called lists and trees, but more on that in the time to come. So an array in Scratch gives us this capability. We give the array a name. It's called a list in the context of Scratch. And then we can use this block at top. Add something to inventory. Delete 1 from inventory. Insert thing, a string, at location 1 of inventory. In other words, and we won't spend too much time on using these now because you might not need them. But if you find ultimately that you kind of need to keep an arbitrary amount of information around, well, the data structure you use to make that happen in general is this thing called an array. Well, let's see this for real. So this is actually a program that is a role-playing game of sorts. It's called Fruitcraft, a play on Warcraft, if you're familiar. Let me go ahead and full screen this one here. Click play, and we have a little animation, it seems. All right, you can move me with the arrow keys. So just as our little DDR game let me move, notice, and actually, so the goal is to look for fruit. So like an idiot, I kind of did this the first time. Apparently, this is a picture of fruit. So there's clearly some bugs, if you will, or at least some disregard for our three-dimensional world here. So I'm going to go around or over or through the table. I'm going to follow this arrow. I'm just using my arrow keys right now. All right, so OK. There we go. So now notice at top left, Scratch is showing me what is inside my list, aka array. Now I have cherries and orange. Oh, this looks interesting. Let me go here. Oh, OK, so we have, remember, some sensing. So remember, just as I'm able to sense is the sprite touching my mouse pointer, I can also sense is a sprite touching another sprite. Is this person touching the sign? If so, do something. And even though we might not know all the blocks that we need to make that happen, it's these basic fundamentals, right? An if condition that says if touching, then say, and then when not touching, don't say. So hide that text. All right, so let me go and pick up these things. Oh, pineapple, bananas, another apple. Hopefully this is the right place. OK, interesting. Great job. You brought cherries, orange, pineapple, bananas, apple. Here's your fruit platter. OK, so simple, but again, demonstrates where you might, in a fairly compelling context, actually need some kind of variable amount of storage. Well, let's make this more sophisticated still. So, and this is actually a topic that you can't traditionally get to in the first week of a course, let alone an entire semester sometimes, this notion of threading. Because a lot of languages, whether it's C or Java, really don't make it easy to do what we're about to do, and frankly, what we've been doing, which is having multiple things happen at once. So the program I wrote earlier that was very underwhelming, hello world, just printing it to the screen, that's kind of the only thing it did. I could add another printf line, another printf line, another printf line, but those are all going to happen in series, not in parallel at the same time. I'm going to get one output, one output, one output. So what's nice about Scratch is that you can have the cat moving, you can have a sheep doing something, you can have this guy, this character interacting with the guy behind the counter. You have a multi-threaded environment. Well, what is a thread? A thread is like a miniature program that's running inside the context of a larger program, and they can operate what essentially looks like simultaneously. Now, this is a bit of a white lie, because ultimately, and we'll talk about this toward the end of the course, many computers have just one CPU, central processing unit, the brains of the computer. When it says Intel inside, it means there's an Intel CPU inside. Well, if a computer only has one brain or one CPU, the reality is that computer can only do one thing at a time. But the neat thing is, when you have a gigahertz, so in other words, a hertz, something happening once per second. And you can think of there being a clock inside of your own CPU. So if you have a 1 gigahertz CPU, there's a little clock or a little crystal that's oscillating a billion times, giga meaning billion, a billion times per second. Well, my God, if you can do something that fast, clicking your fingers a billion times per second, surely we can dupe humans into thinking that two things are happening simultaneously. So if you've ever run AOL Instant Messenger in a window, and also Microsoft Word, and a browser window, and any number of other programs, you are multitasking, but realize that you don't have to quit one of those programs to load the other. You're running them all simultaneously. But what Windows is doing, what Mac OS is doing, is just giving every one of those programs only a split second of computation in the CPU, a split second of attention. But because it does it here, 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 then here, 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 where each of these things is a different program running in your taskbar, you, the human, being the slowest piece of this puzzle, have the illusion of, oh, I am running multiple programs at once. Those of you with iPhones might be somewhat annoyed these days that Apple doesn't support background applications, or at least written by other people besides Apple. In other words, you can't run one program and then use another at the same time if they're written by people in the App Store. And that's because Apple has essentially said users may not run multiple threads simultaneously unless we, Apple, implemented those threads ourselves, unless we wrote the code. Now, this is partly because the battery life of this thing kind of sucks right now. And if you allow people to write programs that run in the background, probably the concern they have is that you're going to drain people's batteries, and most people out there don't understand what a thread is, and they don't care, and they shouldn't have to care. But that's Apple's way, probably, at least in part, of dealing with that issue of multi-threading, being expensive in terms of battery. So here is a thread. So move1.sb tells us to do the following. When the green flag is clicked, go to x, y. So it turns out this whole time that stage can be modeled in fancy terms as like a Cartesian plane, where you have x coordinates and y, right? Just like in mathematics. So 0, 0 is pixel location 0, 0, the little dot somewhere on that stage. Point in direction 90 degrees. So that's either here, 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 here. We'll see once we orient ourselves. And then forever do the following. If touching the edge, play sound, this could be interesting, until done, turn 180 degrees, move 5 steps, and then do it again and again, because it's inside the forever loop. So this is move1.sb. So let me go down to this, move1.sb, I'll go ahead and full screen it again. Hit play.
Ah! 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 Ah!
I don't know if this is like a pedagogical technique or just a bad habit, but it seems if you write programs that are loud and annoying, people remember them. So be it. So this is the sprite. Notice I've changed his costume. How? Well, I probably went up here. I clicked costumes. I futzed around with paint or importing a JPEG or whatever. Sort of uninteresting details intellectually, but that you're nonetheless welcome to play with and procrastinate with for Project Zero. But I've made a duck that orients himself 90 degrees, and he starts moving. So this notion of walking is really about moving some number of steps, some number of pixels. And then notice, because I'm doing this again and again and again forever, I'm constantly checking, am I touching the edge? Am I touching the edge? If so, yell, then turn yourself around and do it again. So again, not a very interactive program, but all these simple puzzle pieces, all these simple building blocks we've been looking at are really what comprised Anne's DDR-like game and Andrew's Raining Men and some of the other more sophisticated programs that you'll write. So here's one that actually is multi-threaded. That was just one duck doing his own thing. Now we'll see a bird and a cat, each of which is a sprite in Scratch speak, and each of which has its own script. So notice in this program, move2.sb, I'm actually going to have two different scripts, each associated with a different sprite. So I've highlighted cat at the moment. Here is the cat script. If I click bird, here is the bird script, and they are clearly different. Well, how are they different? Well, let's look at the cat first. The cat is doing this. Go to -160, -160. Why? Well, again, I was kind of futzing around one day, and I decided, let's have the cat start there specifically. Trial and error in this case. Point and direction. Well, I wanted this demo to be a little different each time. Otherwise, it's really uninteresting. So pick a random degree between 91 and 179. Then forever do the following. If touching bird, here's where it gets fun, play sound, that particular sound, line 4, and then stop the script. In other words, game over is the implication there. Exit, quit. Otherwise, no, actually, I misspoke. It's not an else. It's not an otherwise. But no matter what, point yourself toward the bird and move one step. So in other words, if you're touching the bird, play the sound and quit. Game over. No matter what, though, proceed to point toward the bird and move one step. And actually, it is implicitly an if-else because of the termination. So I retract my retraction. So let's take a look at the bird. What is the bird doing? The bird's not doing all that much. The bird starts at a hard-coded place. And I only did this because it'd be really stupid if the bird might pseudo-randomly start on top of the cat, and then the game has no point. So I go to this location, which I know is different from the cat, point in 45-degree direction, and then forever. Now notice what I did. It turns out with Boolean expressions, not only can you check for true or false, you can flip the meaning. So there's a block called not, which inverts meaning, which is good because I want to do forever, the following forever, if I'm not touching the cat, move 3 steps, but if I'm on the edge, bounce. So you'll also see in Scratch, for user friendliness, sometimes they merge the notion of a condition and a statement like this. So if on edge, bounce, it just happens to be consolidated into 2. So let's play. I'll go ahead and full screen it. I'll go ahead and click the green flag. And notice, this isn't random. The cat is, again, point toward bird. The bird is moving around somewhat randomly, or at least, all right. So kind of sad, but kind of clever nonetheless, at least programmatically. So what more is there? Well, what about if we do something like this? Interesting. So this example, as we'll see, not only uses multiple threads, multiple scripts happening in lockstep, but I'm also using a variable to maintain state and essentially to communicate across the 2 sprites. And this is useful if you effectively want to pass information between the 2. So let me go to version 10 of my Hi program. That's not in this folder. Interesting. All right, well, rather than drag our feet, well, let's go ahead and do... Well, you know what? We're out of tape anyway. Let's go ahead and take a 5-minute break. We'll change tapes and then resume once I found this file. All right. So version 10 has just gone missing. So fortunately, we have the source code here. On the left-hand side, we have a script, a sprite, that just says forever do the following. If muted equals 0, play sound sea lion. think oh hi for 2 seconds, then wait, then repeat. And now notice what the right-hand side is doing. And this is really the only takeaway here, giving ourselves a mean of communication between sprites. On the right-hand side, I have this variable called muted. I set muted to 0. That is false. It is not muted, is the implication. And then forever do the following. If key space pressed, then check the following. If it's muted, set muted to 1, else set muted to 0. So the right-hand side, even though there's some new blocks there, what is that doing in layman's terms, the right-hand side script? It's just toggling the state of this variable, right? We have a forever loop, which just means forever check the following. Is the spacebar pressed? If so, flip the value of muted. So the goal of this exercise here was, again, to have a little fun playing sound. But when I hit the spacebar, it either mutes or effectively unmutes what? Unmutes the other guy. Because he's also happening in lockstep. Whether he's a cat or a bird, it really doesn't matter in this case what the sprite is who's using this script. The left-hand side guy is only going to play the sound sea lion if that value of muted is 0. So in other words, if I hit the space, I make him bark. If I hit it again, it makes him stop. And this just goes on in perpetuity. So it's not such a loss if we haven't that one here. This one's a little more interesting anyway. So I'll go ahead and beat myself up here, if you will. This is actually borrowed from a version of this program someone else wrote. It wasn't called David at the time. I took some liberties since I didn't think it'd be the friendliest thing to have our students punch him in the face. So I swapped in my own face here. And now think about for just a moment what's probably going on underneath the hood here. So I'm apparently moving back and forth as any boxer might. And if I use my arrow keys here, I can start punching and missing. But there we have here. And actually, if we turn this feature here on, notice too, notice my face is clearly changing color. Down. So what's going on? Well, we don't have to even dissect all the pieces, because for the most part, we've presented all the fundamentals. There's more than just one script now, more than just 2. There's actually 4 that belong to the left glove. It looks like there are as many that belong to the right. My own self has this slightly larger one, but it all boils down, if you start to focus on the specifics, and again, all this code will be online, it just boils down to making the computer do what you want it to do. And each of these things are sprites, therefore they can detect themselves. If touching one sprite, do this. And so with these very simple building blocks, almost all of which we've rattled off already, can you do things that are increasingly compelling and much more interesting than just hello world? Well, this is one final functionality that's provided by Scratch and is not often found in at least introductory courses, and this notion of events. We'll actually see this in the context of web programming later in the semester with JavaScript. For C, we won't really play around with this idea, but this example here simply has 2 sprites, each of which has one script. But these guys too can communicate not by using a single variable. So when I discussed a moment ago the notion of muting, that's what we'll call a global variable. Global in the sense that anyone can use or manipulate it. We'll see that that's not often the best practice. But with events, can you do the same thing? You can broadcast an event, and the idea is that any other sprite that wants to listen for that event can somehow respond to it. So in this case here, Marco.sb, we have essentially 2 sprites playing a game with each other. If I go ahead and play this, we'll see on the left-hand side, Marco is waiting forever for me to do what? Hit the space. So I'm going to hit the space. Marco, and now the female says Polo. So why did she say that? Well, let's take a look at her. Oh, when I receive event, say Polo for 2 seconds. So we have cross-thread communication, inter-thread communication, which is useful, yes, to make this simple example happen, but we offer it for today's purposes as a little tool for one's toolkit, so to speak, that if you need 2 sprites to somehow communicate, you've got a couple of options. One, share a variable that both of them check the value of and maybe change, or you have events, which might be a little cleaner than that if you want to send something arbitrary. Well, it turns out that Scratch also supports these things, and in problem set 0, it already is coming in 2 different editions, Standard and Hacker. So the Standard edition, as you'll see when it goes online in PDF form tonight, invites you to pretty much make anything of interest to you so long as it checks off a few boxes. You need to use at least a variable. You need to have at least a few different sprites. You need to use a sound. So we lay some basic ground rules just to kind of push you to do more than scratch the surface. But if you're really the type who wants to get his or her hands dirty very early and maybe do have more of a a more comfortable background, there's these things here. So these are Censor Boards that we bought a whole bunch of for students in the course to use, and they have buttons. They have little sliders that move left to right. They have little inputs that you can connect alligator clips to so that you can check resistance, whether through some physical medium like yourself, left hand and right hand, water, metal, anything like that. There's a light sensor. There's an audio sensor. And so these things too, very simple ideas. Take in sound, do something with it. You can actually detect it programmatically within the program. So this one is actually a simple example of precisely this, singer.sb. Let me go ahead and open this one here. I'll full screen him. He doesn't do all that much, and here we go. He responds to sounds. Now, he also responds to this, and now it just looks like I'm talking. So it's not terribly sensitive to different types of speech, but we're clearly responding to, still responding to something a little binary in nature. I wonder how long we could give lecture like and see how distracting that is. All right. So this one was, let me go ahead and full screen this one. But we'll need to raise the house lights again. Can we pull them down again? So it is, in fact, a light sensor. And the game gets a little freaky when the lights go down. So that was actually unintentional the first time. Normally I use my hand, but taking down Sanders Theater's lights also works as well there. Well, we have one other here. So this one was particularly sophisticated, but again speaks to the relative complexity you can create with what is ultimately quite simple building blocks. This is one by David Wu, now a junior. I'm going to click green flag here. This one uses the little sensor bar to move this guy back and forth. And the goal is, I think, to get the bananas and not get hit by these, the monkey stun counter has just gone up, which means for like 174 milliseconds or whatever, I'm stunned. And he's not responding now. Notice his eyes. So that's bad. Okay. So that actually uses the slider back and forth, but this one actually has some notion of a friction coefficient. So it's not just going left and right in response to me. He kind of skids out on what is ultimately supposed to be ice. So again, very simple primitives, right? Light on, light off, sound on, sound off, slider left, slider right. But even Scratch can interface with this. So realize that for problem set 0, the hacker edition is by nature meant to be very, very accessible. And we have over 100 or 200 of these things out in the hall that you'll be able to collect today and at any office hours next week for problem set 0. So this is this program now that I promised. This was the first thing that I wrote, and this was one of those either sad or really impressive stories of a late Friday night, 8 hours straight playing this. You'll hear in a moment that I chose a song that is perhaps the most annoying song in the world to play ad nauseum for 8 hours while you debug your own program. But this is a little something called Oscar time. And its source code, too, will be distributed on the course's website, just so that you can see a lot of different interactions going on. So I stole this, actually, from an old piece of software from Mac OS. So back when I was a kid growing up with like a Macintosh SE, there was this plugin called Oscar, and you could install it, and then anytime you drag trash to your trash can, Oscar would pop out, sing a little song, and then go back in, right? Completely amusing for like the first few weeks, first few months, and then you realize this is just, it's a slippery slope. So let me go ahead and play this, perhaps not in its entirety, lest you never again be able to watch Sesame Street, but as the instructions say, drag as much falling trash as you can to Oscar's trash can. So notice this game, too, is going to interact with my keyboard. This is trash. Click. Drag. And I won't go too far, but notice if I pull it into the trash quickly, the trash reappears. And now notice it's appearing in a different place each time. So even this game is using some pseudo-randomness. And what we'll see is that this gets progressively faster and progressively faster, much like the DDR game before. So I thought a fun note, perhaps, to conclude on is this. Throughout today, we've been dragging and dropping puzzle pieces. It's a very intuitive language. Problem set 0 will task you with precisely that, implementing the program that most amuses you. We spoke of cell phones earlier today, albeit in the context of iPhones. Yes, it is the case, if you read this morning's Crimson, that Google very kindly donated some 20 telephones to CS50 and CS1 so that we could empower some of you, if you so desire, at term's end, to implement any final project that you want, but also one, if you so choose, on what's called an Android cell phone, marketed by T-Mobile and some other folks throughout the world. Well, we read this article. The Crimson has always been very good to us in recent years press-wise. We were quite flattered that they took an interest in this project, but we were also quite amused. And within minutes of this article going online, it's on the front page of today's Crimson, I got this note here, whose names and such have been redacted. So let's be clear. This is the email I got. So then I got a little curious, right? So I'm like, OK, interesting. There's an article here about CS50, so thecrimson.com. OK, yep, we are, in fact, on the front page there, as well as in the print version. So what you hopefully realized today, paragraph 2, look for it. So bless their hearts, right? This is, in fact, drag and drop programming that you will be focusing on for problem set 0. But I did think, in fairness, because again, we're big fans, and frankly, a lot of our team members are on the Crimson, so it's all good. I did think that I could at least make this so. So instead of Oscar time, which drops this trash, I went ahead and decided we could do this. You know, so I'm going to go to the trash here, some little on-the-fly programming. You know what? I need a different costume here. I'm going to click Import. I kind of prepared in advance here. I'm going to go to my desktop folder. I'm going to go into my 0 folder where I hid it. I've got a little costume here. So if you will, let me go to this thing here. I'm going to go ahead and click this button to shrink him down a little bit. You have the ability to rotate sprites, as you'll see. I'm going to tell it not to rotate anymore. And now if we could crank the volume up just a little bit, we have for you, in conclusion today, drag and drop programming. We'll see you on Wednesday.
If you really want to see something trashy, look at this. I have here a sneaker that's tattered and worn. It's all full of holes and the laces are torn. A gift from my mother the day I was born. I love it because it's trash.